The morning of July 18th, 1943. Philadelphia Naval Shipyard. The air tastes of salt and burning metal. A young man named Thomas Wroblewski crouches beside a massive steel track embedded in the flight deck of USS Bunker Hill, running his gloved hand along a weld seam that every naval engineer in America would call wrong. The joint looks irregular, almost organic, like a river of frozen metal flowing across the surface, rather than the precise geometric pattern demanded by Navy specifications. In 6 hours, this carrier will begin sea trials. In 6 hours, these welds will face forces that have shattered identical joints on every Essex-class carrier built so far. And if they fail, Thomas Wroblewski will face a court-martial for violating naval engineering procedure. But if they hold, he will have solved the problem that has delayed American carrier operations by months and cost the Navy millions of dollars in repairs. This is not a story about admirals or fighter pilots. This is not about grand strategy or famous battles. This is about a Polish welder from Michigan who looked at the most advanced naval technology in the world and realized that everyone, the engineers at MIT, the officers at the Bureau of Ships, the experts who wrote the technical manuals, was wrong. And he was right. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. By the summer of 1943, the United States was building aircraft carriers faster than any nation in history. The Essex-class program called for 24 ships, each capable of carrying 90 aircraft, each designed to dominate the vast distances of the Pacific Ocean. These carriers represented the cutting edge of naval engineering, incorporating lessons learned from the early disasters at Coral Sea and Midway. But they had a critical flaw that threatened to undermine their entire purpose. The hydraulic catapults that launched aircraft from their decks kept breaking. Not occasionally. Repeatedly. Systematically. The catapult system was elegant in theory. Massive hydraulic pistons connected to a shuttle that ran along 2 parallel steel tracks embedded in the flight deck. The shuttle hooked to an aircraft's landing gear, and when the catapult fired, it hurled a 5-ton Hellcat fighter from 0 to 80 miles per hour in less than 300 feet. The entire system depended on the integrity of the welds connecting those tracks to the deck. Under the enormous stress of repeated launches, those welds were failing. They cracked. They separated. They tore the steel deck plating. USS Essex herself, the lead ship of the class, had experienced catastrophic catapult failures during her first sea trials in March of 1943, failures that delayed her deployment by 6 weeks at a time when every carrier was desperately needed in the Pacific. The Navy threw resources at the problem. Engineers at the Bureau of Ships analyzed the metallurgy. They increased the thickness of the steel. They specified more welds, closer together, reinforced with additional brackets. Nothing worked reliably. The welds were done exactly according to naval specifications, approved by multiple inspectors, certified by commissioned officers. And they still failed. Admiral Ernest King, Chief of Naval Operations, reportedly told his staff that the Navy was building the finest carriers in the world, but couldn't get the aircraft off the deck. The problem wasn't the design of the catapults. It wasn't the quality of the steel. It wasn't even the skill of the welders. The problem was the welding technique itself, the very method prescribed in every naval engineering manual. Thomas Wroblewski had never read those manuals. He learned to weld in the back alleys of Hamtramck, a Polish neighborhood embedded in Detroit where the automotive factories ran 3 shifts. The smell of burning metal was as common as the smell of bread from the bakeries. Born in 1916, Tommy grew up watching his father come home from the Dodge main plant with blackened hands and a rattling cough. At 14, he lied about his age to get work at a small fabrication shop on Jos Kampow Avenue. The owner, a Ukrainian immigrant named Petro Kovalenko, taught him that welding wasn't about following rules. It was about listening to metal. The official welding techniques taught in trade schools and mandated by engineering specifications created beautiful, symmetrical joints, straight lines of fusion at precise intervals, each bead identical to the last. They looked perfect in a textbook. They also took twice as long as necessary and, more importantly, they didn't account for how metal actually behaves under stress. Metal flexes. It expands when heated. It contracts when cooled. It vibrates under load. A rigid, geometric weld pattern fights against these natural movements, creating stress concentrations at the points where the pattern breaks. Those stress concentrations become cracks. Tommy developed what he called chase welding. Instead of laying down separate, distinct beads in a predetermined pattern, he created a continuous flow of molten metal that followed the grain structure of the steel. The technique produced welds that looked irregular, almost messy. Inspectors hated them, but under stress testing, they held when conventional welds failed. By 1940, at 24 years old, Tommy was the fastest production welder at Briggs Manufacturing, completing automobile frames in half the time of his colleagues. His supervisor, an engineer named Harold Steinberg, regularly made him redo his work because it didn't match the specification drawings, even though it passed every structural test. Then came December 7th, 1941. Pearl Harbor. Everything changed. Within weeks, automotive plants across Detroit were converting to war production. Within months, Tommy received his draft notice. The Navy, reviewing his employment history, assigned him to the Construction Corps as a certified welder and shipped him to Philadelphia Naval Shipyard, where the first Essex-class carriers were rising on the building ways like steel mountains. He reported to USS Essex in February of 1942. The ship was still under construction, her massive hull plated but not yet fitted out, her flight deck a maze of equipment and workers. Tommy was assigned to a welding crew working on the catapult track installation. On his second day, he examined the welds connecting the tracks to the deck and immediately saw the problem. The pattern was rigid, geometric, and symmetrical. It was textbook perfect, and it was completely wrong for the application. "These are going to crack," he told his supervisor, a chief petty officer named Morrison. Morrison looked at him with the expression of a man confronting stupidity. "Those welds are done to naval engineering specifications. They've been approved by 3 inspectors and a commissioned officer." "They're still going to crack," Tommy said. "The metal needs to flex. These welds won't let it." "Seaman," Morrison said, his voice taking on the edge that career Navy men used when addressing contradiction. "You've been here 2 days. Don't tell me how to build a carrier." Tommy went back to work, following the specifications exactly. 3 months later, during Essex's sea trials, 2 of the 4 catapult tracks developed stress fractures in their mounting welds, exactly where Tommy had predicted. The ship returned to Philadelphia for repairs, delaying her deployment by 6 weeks while the Pacific Fleet desperately needed every carrier it could get. The Navy launched an investigation focused on material defects and temperature stress. No one questioned the welding technique itself, because the technique was standard Navy procedure, approved at the highest levels of the Bureau of Ships. Tommy Wroblewski said nothing. He was a seaman, the lowest enlisted rank. Who would listen? But at night, on his off-duty hours, he began conducting his own tests. The Philadelphia shipyard had a training facility where welders could practice on scrap metal. Tommy requisitioned sections of deck plating and catapult track, claiming he wanted to improve his skills. What he actually did was build test samples. He welded joints using the Navy specification method. He welded identical joints using his chase technique. Then he subjected both to stress testing using hydraulic jacks borrowed from the motor pool to simulate the forces of a catapult launch. The Navy specification welds failed after 200 cycles. Tommy's welds were still intact after 800 cycles, when he stopped counting because the hydraulic jacks needed to be returned. He documented everything in a notebook, sketching the weld patterns, recording the failure points, measuring the crack propagation. He knew he had the solution. He also knew that presenting it through official channels would accomplish nothing. A seaman contradicting naval engineers? The idea was absurd, so he decided to prove it the only way available to him. He would repair a catapult using his method without authorization and let the results demonstrate the truth. The opportunity came when USS Intrepid arrived at the shipyard for post-shakedown repairs in May of 1943. One of her catapults had developed stress fractures, not yet catastrophic, but clearly deteriorating. The official repair procedure called for cutting out entire sections of track and re-welding them using the standard method, a job that would take 3 days. Tommy volunteered for the night shift repair crew. The chief in charge, exhausted by the relentless pace of wartime construction, was happy to have an experienced volunteer. Tommy told him he wanted to learn the official repair procedure. What he actually did, working through the night with a small crew who trusted his confidence more than they understood his technique, was implement his own solution. He used chase welding to repair the stress fractures, creating continuous, flowing joints that followed the natural grain of the steel. The welds distributed stress across a wider area rather than concentrating it at geometric points. They looked irregular. They definitely didn't look like Navy standard welds. When the day shift supervisor arrived at 0600 and saw what Tommy had done, his face went white. "What the hell is this?" Lieutenant Kenneth Bradshaw demanded, staring at the repair. "This looks like a snake crawling across the metal. This isn't procedure. This isn't even close to procedure." "Will you test it?" Tommy asked quietly. Bradshaw stared at him. "You're going to be court-martialed. Will you test it first?" Lieutenant Bradshaw was in an impossible position. If he reported what Tommy had done, there would be an in-day TSB investigation. Tommy would face charges, and the repair would have to be completely redone, adding days to an already delayed schedule. But if the unconventional weld actually worked, if it held when standard welds were failing across the fleet, then reporting it would mean admitting he'd allowed a seaman to violate procedure. Bradshaw made a decision that probably saved thousands of lives over the next 3 years. "Fine," he said. "We test it. If it fails, you're done. If it holds, we'll talk." They tested the catapult that afternoon with progressively heavier loads. It was held. They tested it with repeated launches, simulating a combat sortie schedule. It was held. They subjected it to vibration stress that normally cracked welds within hours. It was held. After the 10th successful high-stress test, Bradshaw turned to Tommy with an expression somewhere between anger and amazement. "How did you learn to do that?" "Making car frames in Detroit," Tommy said. "Metal doesn't care about looking pretty. It cares about working." Lieutenant Bradshaw took the problem to his commanding officer, Commander James Haverford, who had the wisdom to recognize that this was larger than protocol or chain of command. Haverford arranged a demonstration. He invited representatives from the Bureau of Ships, senior engineers from the Naval Research Laboratory, and several officers from Admiral King's staff to witness a controlled comparison test. 2 sections of catapult track were prepared, one welded using standard Navy procedure by certified welders with decades of experience, one welded by Tommy Wroblewski using his chase technique. Both were subjected to identical stress testing using equipment that precisely replicated the forces of aircraft launches. The Navy specification weld failed after 193 cycles. Tommy's weld completed 1,000 cycles without failure. At that point, the testing officer stopped the machine because there was no point in continuing. The difference was absolute. A civilian engineer from MIT, named Dr. Robert Hargrove, examined Tommy's weld under magnification, studying the molecular structure of the joint. "This is metallurgically fascinating," he said, his voice carrying the careful neutrality of academic observation. "The continuous bead creates what's essentially a reinforced zone that distributes stress vectors across the entire joint rather than concentrating them at discrete points." "Seaman, where did you study materials engineering?" "I didn't, sir," Tommy said. "I just weld." "Doctor." Hargrove looked up from his magnifying glass. "You just invented a technique that we're going to be teaching in engineering schools for the next 50 years. But not everyone in the room was impressed. Captain Theodore Wilkes, a senior engineer from the Bureau of Ships with 30 years of service, stood with his arms crossed and his face red. "This is unacceptable," he said, his voice tight with barely controlled anger. "We have specifications for a reason. We have standards. You cannot allow enlisted men to simply ignore procedure because they think they know better." Commander Haverford responded carefully. "Sir, with respect, the procedure isn't working. This alternative demonstrably does work. We're losing time and combat capability because of catapult failures across the fleet. Then we modify the procedure through proper channels." Wilkes snapped. "We don't allow welders to freelance on multi-million-dollar warships." The argument continued for 3 hours, voices rising and falling in the conference room while Tommy sat silently, waiting to learn whether his career would end in commendation or court-martial. In the end, a compromise emerged. Tommy's technique would be officially tested on USS Bunker Hill, the next Essex-class carrier scheduled for completion. If the welds performed well during sea trials, the technique would be considered for wider adoption. If they failed, Tommy would face charges for violating procedure. There was no middle ground, Tommy agreed. He didn't have a choice. USS Bunker Hill completed construction in April of 1943 and began sea trials in May. All 4 of her catapults incorporated Tommy's chase welding technique, which shipyard workers were already unofficially calling Wroblewski welding. The trials were designed to stress every system on the carrier to its breaking point. For the catapults, this meant launching aircraft in rapid succession, day and night, in calm seas and rough weather, until something failed or the crew collapsed from exhaustion. Tommy was aboard as a technical observer, though everyone understood his real role. He was the man whose career and possibly freedom depended on welds holding under the most extreme conditions the Navy could create. On the second night of trials, during a launch sequence in heavy seas, one of the catapults developed an unusual vibration. The launch officer immediately ordered a hold. Engineers swarmed the system. Captain Wilkes, who had also come aboard to observe, approached Tommy with an expression of grim satisfaction. "Your weld is failing, seaman." Tommy walked to the catapult and placed his hand on the track, feeling the vibration through his glove. His stomach dropped. The thrumming wasn't normal. Something was wrong. "Permission to examine the weld, sir?" He spent 20 minutes in the darkness with a flashlight and magnifying glass, tracing every inch of the joint he'd created. His hands were steady, but his mind was racing through possibilities. Material defect, improper penetration, contamination in the bead, any of a dozen failures that would prove Wilkes right and end Tommy's Navy career. Then he found it. The weld was perfect. The vibration was coming from a hydraulic mounting bracket that was a 1/4 inch out of alignment, transmitting abnormal force into the track. The weld wasn't failing. It was revealing a problem that would have gone undetected with standard welding until it caused a catastrophic system failure. "Sir," Tommy said to the launch officer, "it's not the weld, it's the hydraulic mount. It's misaligned." The engineers checked. Tommy was right. The mount was realigned. The vibration stopped. The catapult performed flawlessly for the remainder of the trials. Captain Wilkes stood motionless for several seconds, then turned and walked away without speaking. Tommy never saw him again. Over the next 6 weeks, USS Bunker Hill launched 2,847 aircraft from her 4 catapults during the most intensive sea trials ever conducted on an American carrier. Not a single weld failure occurred. After the trials concluded, the catapult systems were completely disassembled and inspected under laboratory conditions. Tommy's welds showed no stress fractures, no microscopic cracks, no degradation of any kind. On July 15, 1943, the Bureau of Ships issued Technical Bulletin 43-0-7, titled Alternative Catapult Track Welding Procedure for Essex-class Carriers. The bulletin described Tommy's technique in technical detail and authorized its use on all future construction and repairs. Seaman Thomas Wroblewski was promoted to Petty Officer 3rd Class and assigned to train other welders in the new procedure. The Navy estimated that 18 Essex-class carriers in various stages of construction would need their catapult systems re-welded. The Bureau of Ships initially projected it would take 6 months to retrain enough welders to handle the work. Tommy proposed a different approach. He suggested intensive training schools at each major shipyard where experienced welders could learn the chase technique in 2 weeks instead of 6 months. The Navy was skeptical. Welding was a skill that took years to master, and these men were being asked to unlearn everything they knew about proper technique. But Tommy argued that these weren't novices. They already understood metallurgy, heat control, and joint preparation. They just needed to trust what the metal was telling them instead of what the textbook prescribed. "It's not about teaching them something new," he explained to the training officer at Philadelphia. "It's about teaching them to stop fighting the metal and start working with it." The Navy authorized a pilot program. Tommy was given 30 experienced welders and 2 weeks to train them. It became the most difficult teaching assignment of his life. These were men older than him, men with more years of experience, men who had been welding since before Tommy was born. And he was telling them that everything they knew about creating a proper joint was wrong for this application. They resisted. The technique felt wrong in their hands. It looked sloppy, unprofessional. It violated every standard they'd spent decades learning to uphold. One welder, a man named Frank Cusimano, who had been welding since 1925, put down his torch after the first demonstration and shook his head. "Kid," he said, his voice carrying both frustration and something like pity. "I've been doing this for 18 years. You're telling me I've been doing it wrong?" "No, sir," Tommy said carefully. "I'm telling you there's a different way for a different application. What you know is right for buildings, for bridges, for structures that don't flex. This is for something that needs to move. The carrier deck flexes. The catapult track flexes. Every time a plane launches, every time a wave hits the hull, the metal moves. If the weld doesn't move with it, it cracks. You've seen it happen. We've all seen it happen." Cusimano picked up his torch again. "Show me one more time." By the end of 2 weeks, 27 of the 30 welders had mastered the technique well enough to pass certification. The 3 who couldn't adapt were quietly reassigned to other work where conventional methods were appropriate. The training program expanded to Brooklyn Naval Yard, Norfolk Naval Shipyard, and Mare Island on the West Coast. Tommy spent 8 months traveling between facilities, training hundreds of welders, demonstrating the technique again and again to men who initially thought he was either crazy or incompetent. By mid-1944, nearly every welder working on carrier construction had been certified in what was now officially called the Wroblewski technique in internal Navy documents, though it would later be renamed continuous stress compensating bead welding in technical publications. The impact was measurable and immediate. Essex-class carriers that entered service after September of 1943 experienced an 87% reduction in catapult failures compared to the first ships of the class. But the real revolution was in launch times. Before Tommy's innovation, launching a full deck-load strike, the coordinated deployment of fighters, dive bombers, and torpedo planes took between 45 minutes and an hour. Carriers had to carefully schedule launches to avoid having aircraft stacked on the deck, vulnerable to enemy attack while waiting their turn at the catapult. The catapults were supposed to launch one aircraft every 30 seconds. In practice, mechanical failures and the need for constant inspections meant they managed one every 3 to 5 minutes. With welds that didn't crack, that didn't require constant monitoring and emergency repairs, the catapults could finally operate at their designed capacity. By early 1944, Essex-class carriers were routinely launching full strike packages in 12 to 15 minutes. 12 minutes to put 40 aircraft into the air. That capability would prove decisive in the largest naval battle in history. October 25, 1944. The Battle of Leyte Gulf. The Imperial Japanese Navy, in a desperate final gambit to destroy the American landing forces in the Philippines, split its fleet into 3 separate forces attacking from different directions. Admiral William Halsey, commanding the fast carrier task force, took the bait and steamed north to pursue what he thought was the main Japanese carrier fleet. That decision left the landing beaches protected only by a small force of escort carriers, destroyers, and destroyer escorts, vessels never intended to face battleships and cruisers in surface combat. But the Japanese had made a critical miscalculation. They assumed American carriers operated under the same constraints as their own vessels. They expected slow launch times, mechanical breakdowns, and the need for careful coordination. They were wrong. Tommy Wroblewski was aboard USS Essex during the battle, no longer a welder but a chief petty officer serving as a catapult maintenance supervisor. When the call came at 0620 that Japanese carriers had been spotted, he grabbed his tools and headed to the flight deck. What happened over the next 4 hours demonstrated why the forbidden technique mattered. Essex received orders to launch everything she had. Within 12 minutes, 36 Hellcat fighters, 8 Helldiver dive bombers, and 6 Avenger torpedo planes were airborne. USS Lexington matched that performance. So did Intrepid, Bunker Hill, and every other Essex-class carrier in Task Group 38.3. The Japanese carriers, using older catapult systems and suffering from the same reliability problems that had plagued American carriers 2 years earlier, were still getting their first aircraft off their decks when the American strike force arrived overhead. The Battle of Cape Engano became what pilots later called a turkey shoot. But it wasn't just superior pilot training or better aircraft that made the difference. It was the ability to get those aircraft off the deck and into the fight before the enemy could respond. Tommy watched from Essex's flight deck as aircraft returned, landed, were refueled and rearmed, and launched again. The catapults fired continuously. In the heat of battle, there was no time for careful inspections or cautious operations. The systems were pushed beyond their design limits. They held. At one point, a young pilot sprinted past Tommy toward his Hellcat fighter. The pilot paused, turned back. "Chief," he shouted over the roar of engines, "how do these catapults keep working? We've been launching non-stop for 4 hours." Tommy smiled. "Good weld, sir." The pilot laughed and ran to his aircraft. His name was David McCampbell. He would become the Navy's top ace of World War II, credited with 34 aerial victories. He would receive the Medal of Honor for his actions that day. He would never know that the catapult that launched him into combat had been welded using a technique that nearly got its inventor court-martialed. By the end of the Battle of Leyte Gulf, Essex and her sister ships had launched over 500 sorties. Not a single catapult failure occurred. The speed and reliability of American carrier operations was one of the decisive factors in what became the largest naval battle in history, and a catastrophic defeat for the Imperial Japanese Navy. After the battle, Admiral Halsey toured Essex and inspected the catapult systems. He was a battleship officer by training and temperament, uncomfortable with the complexities of carrier aviation, but he understood the results. "Who's responsible for these catapults?" he asked the ship's captain. "Chief Wroblewski, sir." He welded them. Halsey looked at Tommy, taking in the stocky Polish welder from Michigan, who bore no resemblance to anyone's image of a naval hero. "You weld them?" "Yes, sir." "They work very well, Chief." "Thank you, sir." That was the entire conversation. Halsey moved on to inspect other systems. Those 4 sentences, delivered in the noise and chaos of a carrier deck after the largest naval battle in history, were the closest Thomas Wroblewski ever came to official recognition for changing the course of naval warfare. There were no medals, no commendations from the president, no newspaper articles about the welder who solved the catapult problem. The pilots who flew off those decks became famous. The admirals who commanded them became legends. The carriers themselves became symbols of American industrial might. The Polish welder from Hamtramck, who made it all possible, remained anonymous. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. After the war ended in 1945, Tommy returned to Detroit. He went back to welding, but now in the automotive plants that were converting from tank production back to civilian vehicles. He worked for General Motors for 33 years, eventually becoming a senior welding supervisor at the Cadillac plant. He trained hundreds of welders over those decades, always emphasizing the same principle he'd learned in Philadelphia. Listen to the metal, not the manual. When younger workers asked about the continuous bead technique he used, which by the 1960s was being taught in trade schools across the country as standard practice for stress applications, he would shrug. "It's just welding," he'd say. "You do what the metal tells you to do." He never talked much about his Navy service. His wife knew he'd worked on carriers during the war. His children knew he'd received some kind of promotion. But the details remained private, locked away with whatever memories he carried from those years. When someone at the GM plant discovered he was a Navy veteran and asked if he'd seen combat, Tommy's answer was always the same. "I was a welder. I fixed things." It was technically true. It was also a profound understatement. Thomas Wroblewski died in 1997 at the age of 81. His obituary in the Detroit Free Press, 3 paragraphs, on page 12, mentioned that he was a Navy veteran and a retired GM worker. It said he was survived by 3 children and 7 grandchildren. It did not mention carriers or catapults or the thousands of pilots whose lives depended on his welds. The connection might have been lost forever, buried with him in Mount Olivet Cemetery, if not for a historian's curiosity about a technical footnote. Dr. Sarah Chen was researching Essex-class carrier operations for a book on naval aviation logistics when she encountered repeated references in maintenance logs to something called Wroblewski welding, or the Wroblewski technique. The references appeared in documents from 1943 through 1945, always in the context of catapult repairs and modifications. Curious about the origin of the name, Dr. Chen began tracking it backward through technical bulletins and training documents. She found Technical Bulletin 43-0-7 in the National Archives. She found training records from Philadelphia Naval Shipyard listing Thomas Wroblewski as the primary instructor for alternative welding procedures. Finally, she found his personnel file. The file was thin: service dates, promotions, assignment records, a letter of commendation from the Bureau of Ships dated July of 1943. Nothing that explained what he'd actually done or why it mattered. Dr. Chen tracked down his family through military records and death certificates. She found his daughter, Karen Wroblewski Martinez, living in suburban Detroit. Karen agreed to meet, curious about why a historian was interested in her father's Navy service. "He never really talked about the war," Karen told Dr. Chen during their first meeting. "I knew he'd been in the Navy. I knew he worked on ships, but he never made it sound important, just a job he'd done a long time ago." She showed Dr. Chen her father's sea bag, preserved in a closet with his other Navy belongings. Inside were his uniforms, his tools, and several notebooks filled with sketches and calculations. Dr. Chen opened the first notebook and recognized immediately what she was looking at. These were the original tests Tommy had conducted in Philadelphia in 1942. The stress calculations, the failure point measurements, the detailed drawings of weld patterns showing the development of the chase technique. This was the documentary evidence of how one welder had solved a problem that had stumped naval engineers across the country. "Your father, Dr. Chen said carefully, probably saved thousands of lives. The pilots who flew off Essex-class carriers, the ones who fought at Leyte Gulf and Okinawa and the Philippine Sea, they flew because your father's welds held. They never knew his name, but they owed him their lives." Karen was quiet for a long moment, looking at the notebooks. I wish he'd known that someone noticed. Dr. Chen's book, The Silent Service, Unknown Heroes of the Essex-class, was published in 2003. The chapter on Tommy Wroblewski was titled The Welder Who Changed Naval Warfare. It won several awards from naval history organizations. The Navy History and Heritage Command added information about the Wroblewski technique to their official Essex-class carrier documentation. In 2009, the Society of Naval Engineers posthumously awarded Tommy their Distinguished Service Award. Karen accepted it at a ceremony in Washington. She gave a brief speech. "My father would have been embarrassed by this attention," she said. "He always said he was just doing his job. But I think he'd be proud to know that something he did mattered, that it helped people. That's all he ever wanted." Today, the welding technique that Tommy Wroblewski developed in a Philadelphia shipyard workshop in 1942 is taught in every welding school in America. It's officially called continuous stress compensating bead welding in engineering textbooks, used for any application where metal faces repeated stress: bridges, aircraft frames, high-rise buildings, spacecraft. Not 1 in 100 welding students knows where it came from. Not 1 in 1,000 knows the name Thomas Wroblewski. The Essex-class carriers that his welds made functional continued serving long after World War II ended. They fought in Korea, they fought in Vietnam. They served as recovery ships for the Apollo moon missions. USS Lexington, the last of the class, wasn't decommissioned until 1991, 48 years after her catapults were welded. She's now a museum ship in Corpus Christi, Texas. Visitors can walk her flight deck and touch the catapult tracks. If you look closely at those tracks, really examine them, you can still see the characteristic pattern of Tommy's welds. Continuous, flowing, following the grain of the metal. They held it for 50 years. There's a footnote in most engineering textbooks that discuss continuous stress compensating bead welding. It reads, "Developed by T. Wroblewski, USN, 1942 to 1943. Just a footnote, a name and a date. But behind that footnote is a human story. A young man from Hamtramck who watched his father come home from the factory every night with blackened hands, who learned to weld in the alleys behind automotive plants, who looked at the most advanced naval technology in the world and realized that everyone with advanced degrees and impressive titles was wrong, who had the courage to prove it, risking court-martial to test a forbidden technique, who changed the course of naval warfare with nothing more than a welding torch and a willingness to trust what the metal told him. On October 25, 1944, at the Battle of Leyte Gulf, USS Essex launched 40 aircraft in 12 minutes. Those aircraft helped turn the tide of the largest naval battle in history. The pilots who flew them were brave, the admirals who commanded them were skilled, the carriers that launched them were marvels of industrial production, but none of it would have worked without welds that held. Tommy Wroblewski knew that. The metal knew that. The thousands of young men who climbed into Hellcat fighters and Helldiver bombers and flew into combat from those catapults, they never knew it. They never knew the name of the Polish welder whose forbidden technique gave them the seconds of advantage that kept them alive. Sometimes the most important innovations come from the people who aren't supposed to innovate, from the welders who are supposed to follow the manual, from the seamen who are supposed to obey orders without question, from the Polish immigrant's son from Michigan who looked at a Navy specification and said quietly, "That's wrong," and then proved it. Not with theories or calculations or academic credentials, with a simple demonstration. A weld that held when the approved method failed. The Navy had a problem. Catapults were breaking. Carriers. Things were delayed. Aircraft couldn't launch fast enough to win battles. The Bureau of Ships had engineers. The Naval Research Laboratory had scientists. MIT had consultants. They all followed the proper procedure. They all created welds that looked perfect in diagrams. And they all failed in practice. Tommy Wroblewski didn't follow the proper procedure. He created welds that looked wrong to every inspector who examined them. And they worked. That's the entire story. That's the profound irony at the heart of this history. The forbidden technique became the standard. The wrong way became the right way. The welder who was threatened with court-martial for violating procedure ended up training hundreds of other welders in that same violation, which was no longer a violation but official Navy policy. Captain Theodore Wilkes, who had argued so strenuously against allowing enlisted men to ignore specifications, never issued a retraction. He never apologized. He simply disappeared from the historical record after July of 1943, presumably reassigned or retired. Robert Hargrove, the MIT engineer who recognized the metallurgical significance of Tommy's technique, went on to teach materials engineering at Stanford for 30 years. He always included a lecture on the Wroblewski weld, though he never met Tommy again after that single demonstration in Philadelphia. Lieutenant Kenneth Bradshaw, the supervisor who made the critical decision to test Tommy's unauthorized repair instead of immediately reporting it, continued serving in the Navy through the Korean War. He retired as a commander in 1956. In an oral history interview conducted in the 1980s, he was asked about the most important decision he'd made during the war. He thought for a moment. "I let a seaman convince me that the book was wrong," he said. "If I'd followed procedure, we'd have lost a lot more pilots." The historical record is filled with stories of admirals and generals, of battles and campaigns, of grand strategies and turning points. Those stories are important. They deserve to be told, but they're incomplete. Behind every famous battle is a logistics network. Behind every successful campaign is a supply chain. Behind every aircraft that launched from a carrier deck is a catapult system. And behind that catapult system, in this particular case, was a Polish welder from Michigan who understood that metal doesn't care about credentials or hierarchy or approved procedures. Metal only cares about physics. Tommy Wroblewski understood physics the way he understood welding, not through academic study, through practice, through observation, through the accumulated experience of thousands of welds in automotive plants where speed mattered and appearance didn't. The American industrial advantage in World War II is usually discussed in terms of production numbers. We built more ships, more aircraft, more tanks than our enemies. We outproduced the Axis powers through superior industrial capacity and resources. That's true. It's also insufficient. Production numbers only matter if the products work, if the carriers break down, if the catapults crack, if the aircraft can't launch, then production numbers are meaningless. Tommy Wroblewski's contribution wasn't to production volume, it was reliable, to make the machines work the way they were supposed to work. That's less dramatic than stories of combat heroism. It doesn't make for inspiring propaganda posters, but it's how wars are actually won. Essex-class carriers participated in every major naval operation in the Pacific from 1943 until the end of the war. They provided air cover for the invasions of the Marshall Islands, the Marianas, the Philippines. They struck at the Japanese home islands. They were present at Tokyo Bay for the surrender ceremony. Over the course of the war, Essex-class carriers launched hundreds of thousands of sorties. The exact number is difficult to calculate because maintenance logs don't always distinguish between catapult launches and deck launches, but conservative estimates put it above 200,000 separate catapult operations. The failure rate after Tommy's technique was implemented was below 3%. Before his technique, it was above 40%. That difference, translated into operational terms, meant that American carriers could maintain continuous air operations in ways that Japanese carriers couldn't match. It meant that when a strike package needed to launch immediately in response to a threat or an opportunity, the catapults worked. It meant that pilots trusted their equipment. That trust matters in combat. When you're climbing into a 5-ton fighter that's about to be hurled off a deck at 80 miles per hour by a hydraulic piston, you need to trust that the machinery works. The pilots who flew off Essex-class carriers had that trust, not because they understood the metallurgy of the catapult welds, not because they'd read Technical Bulletin 43-0-7, but because the catapults worked, consistently, even under extreme conditions. Tommy Wroblewski never met most of the pilots who depended on his work. He knew David McCampbell only from that brief exchange on the flight deck. He never met the thousands of others. He never read their after-action reports or heard their stories. He went below deck after launches and made sure the catapults were maintained. That was his job, making sure the machinery worked so other men could do their jobs. It's not a glamorous role. It's not the subject of war movies or memorial statues. but it's essential. The welds are still there, if you know where to look. USS Lexington in Corpus Christi, USS Yorktown in Charleston, USS Intrepid in New York City. Museum ships now, preserved as floating monuments to the men who served on them and the era that built them. The flight decks are open to visitors. You can stand where pilots stood, waiting for launch. You can see the catapult tracks embedded in the deck. If you crouch down and examine the welds connecting those tracks to the deck plating, you can still see Tommy's work, the continuous beads, the flowing pattern that follows the steel grain, the joints that looked wrong to every inspector but held for 50 years. They're still holding. 79 years after they were created, that's the proof. Not in words or theories or technical papers, in the actual metal, in welds that were supposed to fail but didn't. Thank you for reading. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The morning of August 19th, 1943. 27,000 feet above the German industrial city of Schweinfurt, Oberleutnant Franz Stigler pulls back on the stick of his Messerschmitt Bf 109 and feels the airframe shudder. The thin air at this altitude makes every control input sluggish, every maneuver an exercise in anticipation rather than reaction. Below him, a formation of American B-17 Flying Fortresses drones eastward, their contrails streaking white against the dark earth. Stigler has flown 174 combat missions. He knows the mathematics of air combat as intimately as a pianist knows scales. Altitude equals energy. Energy equals options. The pilot who controls the vertical dimension controls the fight. This is doctrine. This is physics. This is survival. Then he sees them. 4 aircraft climbed toward his position from below. Twin-boomed silhouettes, unmistakably American. Twin-engine fighters, the type his. Intelligence officers have mentioned in briefings with dismissive shrugs. Heavy machines, reconnaissance platforms, perhaps light bombers. Nothing a properly positioned Bf 109 need concern itself with. Stigler checks his altitude advantage. 3,000 feet, textbook positioning. He rolls into a shallow dive to build speed, preparing for a slashing attack that will send these lumbering machines scattering. What happens next will fundamentally alter his understanding of what is possible in the air. The lead American aircraft, a Lockheed P-38 Lightning, does not break formation, does not attempt evasive maneuvers, does not dive away to build speed or turn to present a defensive profile. It climbs. Not gradually. Not struggling against the thin air and the tyranny of gravity that governs every other aircraft Stigler has encountered. It climbs at an angle so steep it appears almost vertical, 3,300 feet per minute. In 40 seconds, Stigler's altitude advantage evaporates. In 60 seconds, the American is above him, rolling inverted, converting that impossible climb into a diving attack with all the accumulated energy Stigler thought belonged exclusively to him. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This is the story of how a radical American aircraft design shattered the Luftwaffe's fundamental assumptions about air combat and how German pilots, among the most skilled and experienced in the world, confronted a machine that operated according to principles they had been taught were impossible. To understand the psychological impact of that August morning, we must first understand the world. Franz Stigler inhabited a world where German technical superiority was not propaganda, but lived experience. September 1st, 1939. When German forces cross into Poland, the Luftwaffe fields approximately 4,000 combat aircraft. The Messerschmitt Bf 109E, the Emil variant, represents the culmination of nearly a decade of focused development. Its Daimler-Benz DB 601 engine produces 1,175 horsepower. It can reach speeds of 354 miles per hour. At low to medium altitudes, it can climb at nearly 3,000 feet per minute. More importantly, it works. The Spanish Civil War provided a proving ground where German engineers refined the design under combat conditions. By the time war comes to Europe, Luftwaffe pilots fly a mature, debugged weapons system, supported by comprehensive tactical doctrine. The results speak with brutal clarity. Poland falls in 5 weeks. The Luftwaffe achieves air superiority so complete that German ground forces operate with near impunity. France, possessing more tanks and a larger army than Germany, collapses in 6 weeks in large part because the Luftwaffe destroys French command and control, interdicts reinforcements, and breaks the coherence of defensive operations. Even against the Royal Air Force flying the excellent Supermarine Spitfire, German pilots hold their own. The Battle of Britain becomes a near-run thing, decided not by technical inferiority, but by operational and strategic factors. By 1941, the Luftwaffe had established a clear hierarchy of capability. The Bf 109 is the standard against which all other fighters are measured. When the Gustav variant, the G-series, enters service in 1942, it represents an incremental improvement of an already superior design. More power, better armament, refined aerodynamics. German pilots have every reason for confidence. They have fought the best Britain can field and survived. They encountered Soviet fighters by the thousands and found them wanting. American aircraft, when they appear, seem laughable by comparison. The Curtiss, P-40 Warhawk, decent enough at low altitude, helpless above 15,000 feet where its Allison engine loses power dramatically. The Bell P-39 Aerocobra, an experimental configuration with the engine mounted behind the pilot, creating vicious spin characteristics that kill American pilots faster than enemy fire. These aircraft arrive in Soviet hands through Lend-Lease, and Soviet pilots quickly learn to avoid combat above medium altitude. The Americans, it seems, have numbers but lack sophistication. This belief extends beyond individual aircraft to encompass broader assumptions about American industry and design philosophy. German engineering culture prizes precision, refinement, incremental improvement of proven concepts. The Bf 109 goes through dozens of variants, each carefully optimized. The Focke-Wulf Fa 190, when it appears in 1941, represents a parallel development, a radial engine design that complements rather than replaces the Messerschmitt. American design philosophy appears chaotic by comparison. Multiple competing designs, corporate rivalry, no clear central doctrine. The Americans seem to throw concepts at the wall to see what sticks. One of those concepts, in development since 1937, is the P-38 Lightning, Burbank, California. June 1937. The United States Army Air Corps issues Circular Proposal X608, a specification for a high-altitude interceptor. The requirements border on fantasy. Reach 20,000 feet in 6 minutes, achieve 400 miles per hour, carry heavy armament, and maintain enough fuel for extended operations. Every major American aviation company examines the specifications and reaches the same conclusion: impossible. The requirements contradict each other at a fundamental level. High speed demands low weight and minimal drag. Range demands fuel capacity, which means weight. High altitude performance demands turbochargers, which add complexity, weight, and drag. Heavy armament adds more weight. Choose 2, perhaps 3 of these requirements, not all of them. At Lockheed's Burbank facility, a 33-year-old engineer named Clarence Leonard Johnson, universally known as Kelly, approaches the problem differently. Johnson has a reputation for unorthodox solutions. He does not begin with existing fighter designs and attempts to optimize them. He begins with the requirements and asks, what would an aircraft look like if we designed it from first principles to meet these specifications? The answer: nothing like any fighter anyone has built before. Johnson's insight is elegant and radical. Use 2 engines. Not because twin-engine fighters are inherently superior, conventional wisdom holds they are inferior, but because 2 engines solve multiple problems simultaneously. Power. 2 Allison V17 10 engines provide 2,600 horsepower combined later. Variants will push this to 3,200 horsepower. This is roughly double the power available to any single-engine fighter. Redundancy. Lose 1 engine, the aircraft remains controllable and can return to base. In single-engine fighters, engine failure over hostile territory means capture or death. Configuration. With engines mounted in separate booms, the central fuselage becomes available for fuel, armament, and the pilot. All weapons mount in the nose, 4 50-caliber machine guns and one 20mm cannon, meaning all bullets travel parallel paths. No convergence issues, no need to adjust for different ballistic trajectories. Turbochargers. Each engine gets its own General Electric turbocharger, maintaining sea-level power output at altitude. This is technology the Germans will never successfully implement in their fighters. But the configuration creates its own challenges. Twin booms mean twin vertical stabilizers, the distinctive forked tail that will give the aircraft its German nickname. The central nacelle creates unusual aerodynamic characteristics. The long moment arm between engines and fuselage means engine-out handling requires careful design. Kelly Johnson's team spends 2 years solving these problems. January 27th, 1939. Lieutenant Ben Kelsey takes the XP-38 prototype airborne for its first flight from March Field in California. The test is brief, less than 30 minutes, but reveals the aircraft's extraordinary performance. Kelsey reports handling characteristics unlike anything he has flown. The twin-engine configuration provides smooth, stable flight. The turbocharged Allisons deliver power without the harsh vibrations of radial engines. 2 weeks later, Kelsey attempts a transcontinental speed record flight. He makes it from California to Ohio in 7 hours and 2 minutes, an average speed of 350 miles per hour, faster than any fighter's maximum speed. Then, preparing to land at Wright Field, an error in cold weather fuel management causes both engines to quit. Kelsey belly lands the prototype on a golf course. The aircraft was destroyed. This could have ended the program. Instead, the Army ordered 13 pre-production aircraft for evaluation. The production version, designated YP-38, begins flight testing in 1940. Test pilots discover performance that seems to violate conventional fighter wisdom. Top speed, 413 miles per hour at 25,000 feet. Service ceiling, 39,000 feet. Rate of climb, 3,300 feet per minute at sea level, and critically climb rate barely degrades at altitude because the turbochargers maintain engine power. But there are problems. At high speed in a dive, the P-38 experiences compressibility effects. Transonic airflow over the wing creates shock waves that lock the controls. Several test pilots die attempting to recover from terminal velocity dives. The solution hydraulically boosted dive flaps will not arrive until later variants. The aircraft is expensive, $83,000 per unit compared to $55,000 for a P-47 Thunderbolt. It is complex. Maintenance crews must learn to service 2 engines, 2 turbochargers, 2 of everything. Production is slow. When Pearl Harbor exploded in American neutrality on December 7, 1941, the Army Air Forces possessed fewer than 100 P-38s. Most remain in the United States for training and evaluation. The first P-38s to see combat deploy to the Pacific, where they prove effective against Japanese fighters. The lightning speed and firepower give American pilots an advantage over the more maneuverable but lightly armed Zero. In the hands of skilled pilots like Richard Bong and Thomas Maguire, the P-38 becomes a formidable weapon. But the Pacific is a sideshow compared to Europe. By 1943, the air war over Europe had reached a crisis point. The United States 8th Air Force is attempting to prove the doctrine of strategic daylight bombing, the theory that heavily armed bomber formations can penetrate enemy airspace in daylight, strike precision targets, and fight their way home without fighter escort. The theory encounters brutal reality. The Luftwaffe has refined its bomber interception tactics to murderous efficiency. When American bomber formations cross into German airspace, Luftwaffe controllers vector fighter units to intercept. Bf-109 and Fw-190 fighters attack in multiple waves, exploiting the bomber's blind spots. Specially equipped Fu-190A series fighters, the Sturmböcke, or Stormbirds, carry heavy armor and 30mm cannons. They close to point-blank range, absorbing defensive fire, and shred B-17s with weapons designed to kill tanks. The statistics become unsustainable. On the August 17, 1943 Schweinfurt-Regensburg raid, the same mission where Franz Stigler encountered the P-38, the 8th Air Force dispatched 376 B-17s. 60 are shot down. 55 are damaged beyond repair. Over 600 American aircrew were killed or captured. This is a loss rate approaching 20%. At this rate, bomber crews have less than a 1 in 3 chance of surviving their required 25-mission combat tour. The problem is range. Republic P-47 Thunderbolts can escort bombers to the German border, then must turn back for fuel. Royal Air Force Spitfires have even less range. When bombers cross into German airspace, they go alone, and the Luftwaffe is waiting. What the 8th Air Force desperately needs is a fighter that can escort bombers to Berlin and back, a fighter that can fight at 30,000 feet, a fighter that can outclimb German interceptors and deny them the altitude advantage they depend upon. In August 1943, that fighter arrived in England. The P-38H model with improved engines, better turbochargers, and the dive flaps that finally solve the compressibility problem begins operations with the 55th Fighter Group. With drop tanks, combat radius extends to 575 miles. This is enough to reach Berlin, but range means nothing if you cannot fight when you get there. And Luftwaffe intelligence, briefing German pilots on the new American twin-engine fighter, makes critical miscalculations. They know the P-38 has 2 engines. Therefore, it must be heavy, probably 7 tons, compared to the Bf-109's 3 tons. They know twin-engine fighters are slower and less maneuverable than single-engine designs. This is proven doctrine, validated by years of combat experience. They know that altitude advantage is decisive. A lighter, single-engine fighter starting from above will always defeat a heavier twin-engine fighter starting from below. All of these assumptions are logical. All of them are based on sound engineering principles and combat experience. All of them are wrong. August 17, 1943. The Schweinfurt-Regensburg mission is one of the most ambitious operations the 8th Air Force has yet attempted. 230 B-17s will strike ball-bearing factories in Schweinfurt. 146 more will hit the Messerschmitt factory in Regensburg, then continue south to land in North Africa, a one-way shuttle mission. The plan assumes surprise and overwhelming force. It gets neither. German radar picks up the formations assembling over England. Luftwaffe controllers scramble every available fighter unit. By the time the bombers cross the Dutch coast, 300 German fighters are airborne and climbing to intercept. Franz Stigler's unit, Jagdgeschwader 27, scrambles from their base near Munich. Stigler is an experienced pilot, a veteran of campaigns in North Africa and on the Russian front. He has shot down 14 aircraft. He knows his aircraft intimately. The Bf-109 G6 with its DB605 engine producing 1,475 horsepower. He knows its strengths: excellent climb rate at low to medium altitude, good acceleration, deadly accurate 20mm cannon and dual 13mm machine guns. He knows its limitations too. Above 25,000 feet, the mechanically supercharged DB605 begins to lose power. Climb rate degrades. Turn performance suffers as controls become mushy in the thin air. Standard doctrine compensates for this. Gain altitude before the enemy arrives, then dive to attack with speed and energy accumulated from gravity. This gives single-engine fighters lighter, more responsive, decisive advantage over heavier aircraft. At 27,000 feet over Schweinfurt, Stigler spots the bomber formation. Already under attack by other Luftwaffe units, The B-17s maintain tight formation, their overlapping fields of defensive fire creating a deadly crossfire. Then he sees the escorts. 4 aircraft, twin-boomed silhouettes climbing from below. Even at a distance, the configuration is distinctive. P-38 Lightning. Stigler's briefings have covered these aircraft. Heavy. Twin engines mean slower climb, particularly at altitude. Doctrine is clear. Attack from above with speed advantage, make a firing pass, extend away using superior dive performance. He checks his position. 3,000 feet above the P-38s. Perfect altitude advantage. Sun at his back. Textbook. He rolls into a shallow dive, building speed. 400 miles per hour. The Americans are at 24,000 feet, climbing but not rapidly. In 30 seconds, he will be in firing range. Except the Americans are not climbing slowly. The lead, P-38, flown by First Lieutenant Virgil Smith of the 55th Fighter Group, sees Stigler's diving attack. Standard procedure would be to break formation, dive away to build speed, and attempt to outrun the attack. Smith does not break formation. He advances both throttles to war emergency power. 65 inches of manifold pressure, 3,200 horsepower combined. The turbocharged Allisons do not gasp for air at this altitude, they breathe as easily as at sea level. The P-38's nose comes up, not gently, not in a climbing turn to conserve energy, nearly vertical. Stigler, committed to his dive, watches the distance close. 2,000 feet. The P-38 is climbing directly into his attack. This makes no sense. The American should be defensive, should be evading. 1,500 feet. Stigler's rate of closure is slowing. This is impossible. He is diving, building energy. The P-38 is climbing, shedding energy. His closure rate should be increasing. 1,000 feet. The P-38 is still climbing. Stigler can see the pilot's helmet now, can see the twin booms, can see the forked tail. His gun sight tracks center mass. Then, in the space of 10 seconds, physics as Stigler understands it stops working. The P-38's climb rate does not degrade. At 25,000 feet, where Stigler's Bf-109 can manage perhaps 2,000 feet per minute in a climb, the P-38 maintains 3,300 feet per minute. The turbocharged Allisons do not care about thin air. Stigler pulls out of his dive at 26,000 feet, his speed advantage gone. He attempts to climb after the American, but his mechanically supercharged engine is already losing power. The Bf-109's climb rate at this altitude has degraded to perhaps 1,500 feet per minute. The P-38 is at 28,000 feet now, still climbing. 30 seconds later, Smith levels off at 30,000 feet, rolls inverted, and dives. Now he has the altitude advantage. Now he has the energy advantage. Now he has converted Stigler's attack into his own. Stigler breaks hard left, the Bf-109's superior turn rate his only remaining advantage. The P-38 does not attempt to follow in the turn, it would bleed energy, lose the advantage. Instead, Smith uses his speed to zoom back up, repositioning for another attack. This is energy fighting at its purest. Climb, dive, extend, repeat. But it requires an immense power-to-weight ratio to work at high altitude. Single-engine fighters cannot do this effectively above 25,000 feet. Their engines lose too much power. The P-38, with its turbocharged engines maintaining full power, fights at 30,000 feet, the way Stigler's Bf-109 fights at 15,000. The engagement lasts 6 minutes. Stigler never gets a sustained firing opportunity. Every time he maneuvers into position, the P-38 either outclimbs him to reset the engagement or outspeeds him in level flight. Finally, low on fuel and ammunition, Stigler disengages. He dives away one advantage the Bf-109 retains is dive speed and heads for his home field. Behind him, Smith and his flight continue escorting the bombers. That evening, at the Jagdgeschwader 27 debriefing, Stigler tries to explain what happened. He reports, "We had position. We had the attack from above, and they climbed through us. The intelligence officer makes notes. His skepticism is visible. Twin-engine fighters do not outclimb Bf-109s at altitude. This is known. This is physics. But Stigler is not the only pilot reporting this phenomenon. Across the Luftwaffe, after-action reports begin accumulating, from different units, different fronts, different engagements. The language varies, but the observations are consistent. From Jagdgeschwader 2. Encountered P-38s at 26,000 feet. Attempted bounce from above. Enemy aircraft evaded by climbing. Lost one aircraft in subsequent engagement. From Jagdgeschwader 11. The American twin-engine fighter maintains climb performance at altitudes where our aircraft lose effectiveness. Recommend avoiding engagement above 25,000 feet unless numerical superiority is overwhelming. From Jagdgeschwader 26, one of the Luftwaffe's most experienced units. P-38 cannot be treated as a heavy fighter. Climb rate and acceleration comparable to single-engine designs. Standard altitude tactics are ineffective. These are not novice pilots reporting. These are men with hundreds of hours of combat experience, men who have fought Spitfires and P-47s and every Soviet fighter type, men who understand air combat at an intuitive level, and they are all reporting the same thing. The rules have changed. The psychological impact is profound. For 4 years, Luftwaffe doctrine has been built on specific assumptions about energy and altitude. Get above your enemy, dive to attack, extend away, climb back to altitude. Repeat. This works because most aircraft, German or Allied, follow predictable performance curves. Climb rate degrades at altitude. Engine power falls off. Physics applies equally to everyone. The P-38 breaks this equation. And for German pilots accustomed to technical superiority, this is more than a tactical problem. It is a psychological crisis. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Luftwaffe's response to the P-38 reveals the limitations of even excellent organizations when confronted with unexpected technological disruption. The German aviation industry and military leadership cannot simply dismiss the reports too. Many experienced pilots from too many different units are reporting the same phenomena. But accepting the reports means accepting that fundamental assumptions about fighter design are wrong. German engineering culture in the 1940s is built on precision and incremental improvement. The Daimler-Benz DB600 series engine evolves through multiple variants, each carefully optimized. The Messerschmitt Bf-109 undergoes dozens of modifications, each addressing specific performance issues. This approach works well for refining existing designs. It works poorly for paradigm shifts. The P-38 represents a paradigm shift. It is not an improved version of existing fighter philosophy. It is a different philosophy entirely, built around solving a specific problem long-range, high-altitude escort that German designers never prioritized because the Luftwaffe never needed to escort bombers into heavily defended enemy airspace. German intelligence attempts to understand the P-38 by analyzing captured examples and studying reconnaissance photographs. What they see confirms that it is heavy approximately 7 tons combat weight compared to the Bf-109's 3 tons. What they cannot easily understand from external analysis is the turbocharger system. Turbochargers are not new technology. The principle using exhaust gases to drive a compressor that forces more air into the engine is well understood, but implementation is complex. The turbocharger must operate at extreme temperatures. It must maintain precise speed control. It must integrate seamlessly with engine management. American manufacturers, particularly General Electric, have spent years developing reliable turbocharger systems for aviation use. By 1943, the technology is mature. Each Allison V1710 in the P-38 gets its own General Electric Type B13 turbocharger, mounted in the tail boom behind the engine. This placement far from the pilot, with the tail boom acting as a long exhaust duct, helps manage heat. German attempts to develop equivalent systems for fighter engines consistently fail. The DB-600 and Jumo 211 engines use mechanical superchargers, gear-driven compressors that boost pressure but consume engine power and lose effectiveness at high altitude. Various German designs for turbocharged fighter engines run into development problems: overheating, unreliable controls, weight penalties. By 1944, some German high-altitude interceptors, like the Ta-152H, received experimental turbocharger systems, but these arrived too late and in too few numbers to affect the war. The result is that German fighters operate on one performance curve and the P-38 operates on another. Consider the numbers. A Bf-109G6 at full military power climbs at approximately 3,000 feet per minute at sea level. At 15,000 feet, this drops to perhaps 2,200 feet per minute. At 25,000 feet, perhaps 1,500 feet per minute. At 30,000 feet, below 1,000 feet per minute, the P-38J, the definitive production variant, climbs at 3,300 feet per minute at sea level. At 15,000 feet, 3,000 feet per minute. At 25,000 feet, still 2,800 feet per minute. The turbocharged engines maintain sea-level power output up to 28,000 feet. This is not a small advantage. This is an overwhelming advantage in the vertical dimension. German tactical doctrine attempts to adapt. New instructions go out to fighter units. Avoid engagement with P-38s below 25,000 feet unless you have overwhelming numerical advantage. Do not attack from below. If attacked by P-38s, dive away, do not attempt to climb. Engage only if you can maintain altitude parity. These are defensive tactics. The Luftwaffe, which spent the first 3 years of the war dictating the terms of air combat, is now reacting to American capabilities. Individual pilots develop their own methods. Some refuse to engage P-38s at all, preferring to attack bombers and avoid the escorts. Some attempt to use their superior turn rate to force the P-38s into slow-speed turning fights, where engine power matters less than wing loading and control response. But these are tactics of desperation, not tactics of superiority. The human cost of this technological shift appears in individual combat reports and pilot accounts. Consider the experience of Lieutenant Herbert Huppertz, a pilot with Jagdgeschwader 51, March 11, 1944. Huppertz's unit scrambles to intercept a bomber formation approaching Leipzig. He climbs to 28,000 feet higher than comfortable, where his Bf-109 G14 handles poorly, but necessary, to get above the escorts. He spots 4 P-38s below, at 24,000 feet. Standard doctrine: dive to attack, use speed to make a single pass, then extend away before they can respond. Huppertz rolls into his dive. The lead P-38 sees him coming, the distinctive twin-boom silhouette is hard to hide and pulls into a climb. Huppertz is diving at 450 miles per hour. The P-38 should not be able to climb fast enough to evade. But it does. The American pilot converts his forward speed into a zoom climb, pure energy management, and by the time Huppertz pulls out of his dive at 26,000 feet, the P-38 is at his altitude and turning toward him. Huppertz attempts to climb back to altitude. His Bf-109 struggles. The engine is at full military power, but at this altitude it produces perhaps 1,000 horsepower, 30% less than at sea level. The P-38's turbocharged Allisons produce full power. The American pilot climbs easily, positions for a deflection shot. Huppertz realizes he cannot outclimb the American. He cannot outrun the American in level flight. His only option is to dive trade altitude for speed, disengage, return to base. He survives. But he has been driven from the combat area without firing a shot, driven away by an aircraft he was supposed to have a tactical advantage over. His after-action report is terse. Encountered P-38 at high altitude, unable to maintain engagement. Disengaged. This happens dozens of times daily across the German defensive frontier. The strategic implications extend beyond individual dogfights. By late 1943, P-38s were escorting bomber formations deep into German territory. The 8th Air Force's campaign of strategic bombing nearly abandoned after the catastrophic losses of August and October 1943 receives new life. The mathematics of bomber attrition changed dramatically. In missions with P-38 escort, bomber loss rates drop below 5%. In missions without escort, losses remain above 10%. This is not just about protecting bombers. This is about the Luftwaffe's finite resources. Every engagement with P-38s costs German fighters. Not necessarily an aircraft destroyed, though the P-38's heavy nose armament makes it lethal in head-on attacks, but in fuel consumed, ammunition expended, and opportunities missed. When Luftwaffe fighters must focus on avoiding P-38 escorts, they cannot effectively attack bombers. When they must burn fuel climbing above 30,000 feet to get altitude advantage, they have less time on station. When they must disengage from combat to avoid being outclimbed, they cede the initiative. The Luftwaffe is being forced into a war of attrition it cannot win. German industrial production, impressive as it is, cannot match American output. In 1944, German factories produced approximately 40,000 aircraft of all types. American factories produce nearly 100,000. More critically, the Luftwaffe is losing experienced pilots faster than the training system can replace them. A pilot shot down over Germany, even if he survives, is often injured, requiring weeks or months to recover. An American pilot shot down over Germany is lost permanently, either killed or captured. But America has a larger population base and a more robust training pipeline. The exchange rate favors America. By early 1944, average Luftwaffe pilot training had dropped to less than 150 hours before assignment to combat units. In 1940, new pilots received 250 to 300 hours of training. American pilots in 1944 receive over 300 hours of training, including 50 to 70 hours in type in the actual aircraft they will fly in combat. The Luftwaffe is fielding increasingly inexperienced pilots in obsolescent aircraft against increasingly experienced American pilots in superior aircraft. This is not a sustainable equation. Individual American pilots begin to exploit the P-38's unique capabilities in innovative ways. Major Richard Ira Bong, operating in the Pacific Theater, develops tactics specifically built around vertical energy management. When engaged by Japanese fighters, typically the Mitsubishi A6M0, a highly maneuverable but lightly built aircraft, Bong does not attempt to turn with them. The Zero can outturn any American fighter at low to medium speeds. Instead, Bong uses the P-38's speed to maintain separation, then converts that speed into a zoom climb when attacked. The Zero tries to follow. At 8,000 feet, the Zero is still climbing. Well, it is light and has good power to wait at low altitude. At 12,000 feet, it is beginning to struggle. At 15,000 feet, it is nearly stalling, wallowing in the thin air. The P-38, meanwhile, is still climbing at nearly full power. Bong rolls over the top of the climb, dives back down with gravity and 3,000 horsepower assisting, and the Zero has no time to react. The engagement is over in seconds. Bong uses this tactic to shoot down 40 Japanese aircraft, becoming America's highest-scoring ace. He was killed in August 1945, not in combat, but testing a new jet aircraft. He is 24 years old. In Europe, pilots develop different tactics for different threats. Against the Bf-109, the preferred method is to bait German pilots into climbing fights they cannot win. Against the WW-190, which has better roll rate and dive performance than the Bf-109, the tactic is to use the P-38's superior high-altitude performance to force engagements above 25,000 feet, where the full 190's BMW 801 radial engine loses effectiveness. Some of the most successful P-38 pilots never become household names. They are men who understand energy management, who think in 3 dimensions, who use their aircraft's strengths and avoid its weaknesses. The P-38 is not invulnerable. It is large, easy to spot. In a slow-speed turning fight, a skilled German pilot in a Bf-109 or FW-190 can potentially outmaneuver it. The P-38's size makes it vulnerable to hits, though the twin-engine configuration means it can often survive damage that would down a single-engine fighter. But these vulnerabilities matter less when the P-38 can dictate the terms of engagement, when it can choose to fight or flee based on energy advantage, when it can climb away from threats that would be lethal to other aircraft. The German response, by 1944, increasingly focuses on avoiding combat with American escorts entirely. New tactical instructions emphasize attacking bomber formations at moments when escorts are absent or out of position. This requires careful timing and intelligence about American flight routes and escort patterns. It also produces a psychological shift in German fighter units. The Luftwaffe, which began the war with aggressive, offensive doctrine, is now fighting defensively. Pilots are instructed to preserve their aircraft, to avoid unnecessary risks, to disengage rather than press attacks. This is rational from a resource preservation standpoint. Germany cannot afford to lose fighters and pilots at the rates of 1943, but it represents a fundamental concession. The initiative now belongs to the Americans. Some German pilots resist this shift. Aces like Walter Nowotny and Heinz Baer continue to engage Allied fighters aggressively, racking up impressive scores. But these men are exceptional, and their tactics, while individually successful, cannot be replicated across the entire fighter force. Nowotny, with 258 confirmed kills, was shot down and killed in November 1944. He is 23 years old. Baer, who survives the war with 220 kills, later reflects that the air war was lost not because German pilots lacked skill or courage, but because they were outnumbered and flying increasingly obsolescent aircraft against an enemy with unlimited resources. The P-38, in this context, becomes symbolic of a larger reality. American industrial and technical capacity has reached a point where it can field weapons systems that match or exceed German equivalents, while producing them in vastly greater quantities. By mid-1944, the Luftwaffe's situation had become desperate. The invasion of Normandy on June 6 strains German resources further. Fighter units must divide their attention between defending against strategic bombing and supporting ground forces attempting to contain the Allied advance. P-38s, operating from bases in England and later from captured airfields in France, range across German-occupied territory. They escort bombers to targets deep in eastern Germany. They conduct fighter sweeps, actively hunting German fighters. They perform ground attack missions, strafing trains and vehicles. The versatility of the design, a consequence of its power and range, makes it difficult for German commanders to predict where P-38s will appear. A formation that seems to be escorting bombers might break off to attack an airfield. A fighter sweep might encounter German fighters climbing to intercept a different raid. Luftwaffe pilots learn to scan the sky continuously for the distinctive twin-boom silhouette. The German nickname for the aircraft, der Gabelschwanzteufel, the fork-tailed devil, reflects both fear and respect. It is a devil because it appears everywhere, because it cannot be predicted, because it breaks the rules of air combat. American pilots embrace the nickname. Some paint devil imagery on their aircraft. They understand that when your enemy gives your weapon a mythological name, you have won a psychological victory as significant as any tactical success. The final year of the war sees the Luftwaffe attempt several desperate technological responses. The Messerschmitt Me-262 jet fighter, capable of speeds approaching 550 miles per hour, enters service in July 1944. In theory, the jet's speed advantage should allow it to avoid or disengage from any propeller-driven fighter. In practice, the Me-262 has severe limitations. Its Jumo 004 turbojet engines are unreliable, with service lives measured in hours rather than hundreds of hours. The aircraft consumes fuel at prodigious rates, allowing only minutes of combat time. Pilots must slow down to attack bombers, making them vulnerable to escorts during the attack run. P-38 pilots quickly learned to avoid dogfighting with. Me-262s, the speed differential is too great, but to catch them during takeoff or landing when the jets are slow and vulnerable. Several Me-262s are lost this way. The jet program, like many late-war German technological initiatives, arrives too late and in too few numbers. Approximately 1,400 Me-262s are built, but fewer than 300 see combat. Many are destroyed on the ground by Allied bombing. Others were abandoned when fuel supplies collapsed in early 1945. The P-38 continued flying missions until the end of the war in May 1945. The final tallies are impressive. Over 10,000 P-38s, built in all variants, more than 130,000 combat sorties flown in Europe alone, over 1,800 German aircraft destroyed in air-to-air combat in the European theatre. But statistics cannot fully capture the aircraft's impact. The P-38 changed how the air war was fought. It gave American bomber formations survivable deep penetration capability. It forced the Luftwaffe into defensive tactics. It shattered German assumptions about what was possible in fighter design. In the decades after the war, surviving German pilots offered reflections that reveal the lasting psychological impact of encountering the P-38. Franz Stiegler, the pilot from our opening encounter, emigrated to Canada after the war and worked as an aerospace engineer. In interviews late in his life, he spoke candidly about the experience of fighting against American aircraft. "We were told that American fighters were inferior," he said in a 1991 interview, and for a time that was true. The early aircraft they sent, the P-39, the early P-40, were not competitive, but when the P-38 arrived, we realized that American engineering had taken a different path. They had not tried to make a better Messerschmitt. They had solved a different problem entirely. And once we understood that, we also understood that we could not win. Stiegler's words point to a broader truth about technological competition. Superiority is context-dependent. The Bf 109 was an excellent fighter for the missions the Luftwaffe needed to perform in 1939 and 1940. Short-range combat over friendly or contested territory, where it could fight at altitudes, where its engine performed well and returned to base quickly. The P-38 was designed for a different mission, long-range escort at high altitude over enemy territory. It sacrificed some advantages of the Bf 109 lower wing, lighter weight, better turn rate at low altitude to gain advantages. The Bf 109 could not match. Range, high-altitude performance, redundancy, heavy firepower. When the two aircraft met in combat, the question was not which was, objectively better, but which was better suited to the specific circumstances of the engagement. At 30,000 feet over Germany, escorting bombers, the P-38's advantages mattered more than the Bf 109's. This is the nature of technological disruption. It changes which capabilities matter. The P-38's operational history extended beyond Europe and the Pacific. In the Mediterranean theatre, P-38s flew reconnaissance missions over heavily defended targets, using their speed and altitude capability to evade interception. The photo reconnaissance variant, designated 5, lacked armament but carried cameras in the nose. These aircraft produced critical intelligence about German defensive positions, troop movements, and industrial facilities. In North Africa, P-38s provided air cover for the Allied invasion and subsequent campaigns. The desert environment posed unique challenges. Sand and dust wreaked havoc on engines, but the twin-engine configuration provided safety margins single-engine fighters lacked. If one engine ingested sand and failed, the pilot could limp home on the other. In the China-Burma-India theatre, P-38s escorted transport aircraft over the Himalayan hump, the treacherous air route that supplied Chinese forces after the Japanese cut land access. The P-38's high-altitude performance made it well-suited to operations in the thin air over 20,000-foot mountain passes. Each theatre revealed different aspects of the design's versatility, but the fundamental characteristics remained constant: power, range, altitude performance, and the ability to climb at rates that opponents could not match. By war's end, the P-38 had accumulated a complex reputation. In the Pacific, it was widely respected, the preferred mount of America's top aces. In Europe, it had more mixed reviews. Some pilots loved it, others found it complex and temperamental, preferring the simpler P-47 Thunderbolt or the nimble P-51 Mustang. The European criticism had some validity. The P-38 was maintenance-intensive. Its complex turbocharger system required skilled mechanics. In the cold of high-altitude European combat, engines sometimes failed to start, or turbochargers froze. Pilots had to monitor 2 sets of instruments, manage 2 engines. But these were problems of complexity, not fundamental design flaws. And for the mission, it was designed to perform high-altitude escort. It had no equal until the P-51D Mustang arrived in numbers in mid-1944. The Mustang eventually replaced the P-38 as the primary long-range escort fighter in Europe. The Mustang was cheaper to produce, easier to maintain, and with its Packard-built Rolls-Royce Merlin engine, it matched the P-38's high-altitude performance. Being a single-engine design, it was lighter and more agile. But the Mustang's success does not diminish the P-38's impact. The P-38 proved that long-range escort was possible. It demonstrated that turbocharger technology could work reliably in combat. It forced German tactical doctrine to adapt. It bought time for other American designs to mature. In technological competition, being first to solve a problem matters, even if later solutions are more elegant. The legacy of the P-38 extends into post-war aviation development. Kelly Johnson, the aircraft's chief designer, went on to lead Lockheed's Skunk Works, the secretive division responsible for the U-2 spy plane, the SR-71 Blackbird, and the Phone-17 stealth fighter. The design philosophy evident in the P-38 solved difficult problems by questioning conventional assumptions became the Skunk Works' signature approach. The turbocharger technology refined in the P-38 influenced post-war aircraft development. Modern turbofan engines are distant descendants of the General Electric turbochargers, incorporating similar principles of exhaust-driven compression. The lessons of energy management learned by P-38 pilots informed fighter tactics for decades. The concept of using vertical maneuvers to control engagement geometry remains central to air combat doctrine. Modern fighter pilots train in tactics that would be immediately recognizable to Richard Bong or Virgil Smith. Use your energy advantages, avoid your opponent's strengths, control the vertical dimension. Perhaps the most profound legacy is psychological rather than technical. The P-38 demonstrated that technological superiority is not permanent, that assumptions based on past experience can become liabilities when circumstances change, that solving problems sometimes requires abandoning conventional wisdom entirely. For German pilots encountering the P-38 in 1943 and 1944, the experience was disorienting precisely because it violated their understanding of what was possible. They had internalized certain rules about air combat based on years of experience. The P-38 broke those rules. This is the pattern of technological disruption across all domains. New capabilities render old expertise less valuable. New paradigms replace old certainties. Organizations built around existing technology struggle to adapt. The Luftwaffe was not incompetent. Its pilots were skilled, its leaders experienced, its aircraft well designed for their intended purposes. But it was structured around assumptions that worked in 1939 and stopped working by 1943. And rigid institutional structures made adaptation difficult. The United States Army Air Forces, with fewer pre-war institutional commitments and greater resources to experiment, could afford to pursue radical designs like the P-38. When it worked, they produced more. When it didn't, they tried something else. This flexibility, the ability to fail without catastrophic consequences, to experiment with multiple approaches simultaneously proved as important as any specific technical achievement. Today, fewer than a dozen airworthy P-38s remain. They appear at air shows, carefully maintained by dedicated organizations and wealthy collectors. When one takes off, the distinctive sound of two Allison engines synchronized, the twin booms and forked tail unmistakable against the sky, elderly veterans sometimes attend to watch. Some of them flew P-38s, some flew against them. The veterans who flew them remember the complexity, the power, the confidence that came from knowing you could outclimb anything else in the sky. The veterans who flew against them remember the frustration, the disorientation, the moment when assumptions failed and reality proved more complex than doctrine allowed. Both groups remember an aircraft that changed how air combat was fought and challenged, their fundamental beliefs about what was possible. In that sense, the P-38's true legacy is not measured in kills or missions flown, but in the lesson it taught, that engineering creativity combined with industrial capacity can produce capabilities that seem impossible until they appear in the sky above you, climbing at 3,300 feet per minute, breaking every rule you thought governed the physics of flight. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.